So folks, here we're ready to put together this whole theory of solving our nth order linear ODEs. So in this case, we've got a second order non-homogeneous ODE. Notice that it has a non-homogeneous forcing function here, f of x, on that right-hand side. So later on, we'll learn strategies for finding the particular solution to these non-homogeneous ODEs, but for right now, I just want you to verify that this phi of x solves the ODE. So what you'll need to do is you'll take phi of x, which is our minus 4x minus 1. You'll take phi prime of x. You should get minus 4. You'll take phi double prime of x, and you'll get 0. And then I want you to go ahead and plug each one of those into the original ODE and verify that it is indeed a solution. So pause the video and do that. So now that we've verified that this phi of x solves the original non-homogeneous ODE, we'll say that this y sub p is one particular solution to the non-homogeneous ODE. The next question I want to ask is, what is the corresponding homogeneous ODE? Well, in this case, the corresponding homogeneous ODE is y double prime plus y prime minus 6y equals 0. So I would like you to use the characteristic equation technique to find the general solution to the corresponding homogeneous ODE. And this is the work that you'll do from here on out. You'll go ahead and assume that the solutions to y double prime plus y prime minus 6y equals 0 form a what? They form a vector space. And this is the part that we'll prove in class, although sometimes I will ask you to prove this as well. In this case, a second order homogeneous ODE forms a vector space of dimension 2. And the dimension of the vector space for these homogeneous linear ODEs will always match the order of that homogeneous linear ODE. But sometimes I will ask you to prove that. So now you're going to find two solutions to the homogeneous ODE using the characteristic equation technique. So pause the video, take a look at the characteristic equation to this, and find the two solutions. So you should have found that y1 equals e to the minus 3x and y2 equals e to the 2x are two linearly independent solutions. Or excuse me, at this point, all we've done is shown that these are two solutions to the homogeneous ODE, and we now want to show that they are linearly independent by showing that their Wronskian is non-zero for at least one value of x on some interval. And I didn't leave you enough room to do this, so let's go ahead and do it over here. So the Wronskian of these two solutions would be the Wronskian of e to the minus 3x, comma, e to the 2x. And so that Wronskian is the determinant of this matrix right here. E to the minus 3x minus 3e to the minus 3x. Remember, I take the derivative of that first solution, and that shows up there. I'll take I'll list the second solution here, e to the 2x, and I'll take its derivative, 2e to the 2x. So that gives us the Wronskian that we want to compute this determinant of. And in this case, we get 6e, and if we add those two solutions together, we get e to the minus x, and we're going to subtract from that, in this case, negative 3e, adding those two solutions together, e to the minus x, which gives us a positive 3e to the minus x. And this is, in fact, non-zero for all choices of x, which is great. But remember, all we're doing when we're trying to show that these two solutions are linear independent is if we know they already solve a differential equation, it's enough to just find one x value so that they're not zero. So notice that if x equals 0, 3e to the minus 0 is equal to 3, which does not equal 0. And so we have shown that these two solutions are linearly independent. Now, once we have two linearly independent solutions, we can conclude that because the dimension of the vector space was 2, that these two linearly independent solutions form a basis of our solution space. What that means then is that every solution to the corresponding homogeneous differential equation can be written as a linear combination of our basis solutions, our basis vectors. So in this case, the general solution is y sub t equals c1 e to the minus 3t plus c2 e to the positive 2t. And here, just to clarify, because I'm going to use it down below, let me put y sub h. That is the general solution to the homogeneous equation. This should be a minus 18 here, folks. I'll fix it in your notes. So now we can give the general solution not just to the homogeneous ODE, but to the original non-homogeneous ODE, the equation that we were asked for. So our general solution, by the principle of superposition and a few other facts about vector spaces, is that y sub t is equal to y sub h plus y sub p. So our general solution is y sub t equals, and our general solution to the corresponding homogeneous ODE was c1 e to the minus 3t plus c2 e to the positive 2t, plus our one particular solution that we were given in this case, the phi sub x, which is minus 4x minus 1. So this, to clarify, was the general solution to the homogeneous equation. That's what we're calling y sub h. And this was the one particular solution that we were able to come up with to the original non-homogeneous ODE. And these together, in summation, by the second principle of superposition, give us the general solution to our non-homogeneous but linear nth order ODE. Folks, that concludes our discussion of the theory, and now we'll focus on the techniques. I'll see you in class.